Hello there, welcome to my class. Today we'll talk about
Three other combinational circuits that are very important inside our computers are encoders, decoders, and code converters. What are these? Encoders are the circuits that converts any form of data to binary, such as pictures, alphabets, sounds, temperature, and the like. All these informations need to be converted into binary form because it's only binary that can be understood by our computers. Which circuit inside our computer is responsible in converting this information into binary? It is our encoder. That's why we usually hear people saying that when you try to use the keyboard and type, they are saying that you are encoding. Simply because you are trying to convert the alphanumeric character in our keyboard into binary. So how about decoders? Decoders are the one responsible in converting those binary information into their original form. If we try to listen to music, what is being processed by our computer are binary information. Before we could really listen to them in the form of music, it has to be decoded. That's why we have different forms of decoders such as MPEG, 3, 4, and the like. We have also what we call code converters. Code converters are the circuit responsible in converting one binary form to another. Sample of which are what we call BCD code. Our code, the binary code that we are using is usually in the 8421 code. And if we want to convert that into BCD, then we need what we call a code converter. In today's topic, let's try to design these three combinational circuits: encoders, decoders, and code converters. Let's start with the design of encoder. As an example, let's try to design an octal decoder. What is an octal decoder? It is a decoder that will have 8 output because that is an octal decoder. As if saying, we try to convert binary to octal. So since we are trying to convert binary to octal, how many input do we need? For us to represent 8, we need 3 inputs. We will be having as an output the 8 possible symbols that we use in octal, that is 0 to 7. How many combinations? There will be 8. This will be the 8 possible combinations from 00 to 111. And since that is an octal decoder, what is 00? 00 as we know is equal to 0. It's only 0 that will be equal to 1 and the rest will be 0. Then 001 will be equal to 1 and the rest will be 0. So 010 is 2, 011 is 3, 100 is 4, 101 is 5, 6, then 7. How many equations do we need? Definitely we'll be needing 8 equations because we have 8 output. So what's the equation here? So since output has only 1 prime, then that will be equal to 0 will be equal to A prime, B prime, C prime. 1 will be equal to A prime, B prime, C. 2 will be A prime, B, C prime until we reach 7, that is A, B, and C. It is only a mean term. To implement, we have A, B, C. How are we going to implement 0? So that will be A prime, B prime, C prime. So we need only a 3 input AND gate. 3 input AND gate A, B, A prime, B prime, C prime is equal to 0. Then we have 1, A prime, B prime, C, A prime, B, C prime. Then we have A prime, B, C. Then A, B prime, C prime. Then A, B prime, C. Then we have A, B, C prime. Then A, B, C. This octal decoder can be represented as a single block diagram having 3 input and 8 output. That's why an octal decoder is often called 3 by 8 decoder. Let's have also an encoder. If we have an octal decoder, let's have also octal encoder. This time, we are trying to encode. So we convert the octal information into binary. So our input this time is the octal symbols from 0 to 7 and our output will now be binary form. 0 will be 000, 1 will be 001, 2, 010, 3, 011, 4, 1005, 101, 6, 110, and 7 will be 111. How many equations do we need? Definitely we have three output, A, B, and C. So we need the equation for A, B, and C. A will be equal to 4 plus 5 plus 6 plus 7. How about B? It will be 2 plus 3 plus 6 plus 7. And C will be 1 plus 3 plus 5 plus 7. So to implement, we have this time how many input? So we have 8 input. 0 to 7. So what are we going to do? This time we'll be using an OR gate. For A, that will be 4, 5, 6, 7, and entering into A, 4 input, OR gate will be equal to A. Then B, we have 2, 3, 6, and 7. 2, 3, 6, and 7. Then C is 1, 3, 5, and 7. 1, 3, 5, and 7. Let's try to input, for example, 4. So if we are going to input 4, this will be equal to 1. 1, so the rest will be equal to 0. So it's only 4 that will be equal to 1. So 1, since the presence of 1 here will be equal to 1, so this will be 1. The rest is equal to 0. 4 only entered into A, so therefore A will be equal to 1, whereas B and C will be equal to 0. So therefore 1, 0, 0. Is that correct? So 4 is 1, 0, 0. So let's try to have 5, 1, 0, 1. So 5 is here. So 5 is entered into A, so this will be equal to 1. 5 entered in also into C, so this will also be 1. For B, 5 is not present on B, so therefore it's equal to 0. So the answer is 1, 0, 1. Let's have another. How about 7. 7, that is 1. 7 can be seen in C, can be seen also in B, and in A. So therefore, our output will be equal to 1. We were able now to convert our octal information into binary form. Let's deal also with code converters. As an example, let's try to design a 3-bit 2's complementer. We want to get the 2's complement of a 3-bit information. So how many input do we need? Definitely we'll be having 3 inputs. How about the output? Since we are getting the complement, then we will be needing also 3 output. 3 input, there will be 8 possible combination. What's the 2's complement of 0, 0? That is equal to 0, 0, 0. Complement of 0, 0, 1. Retain the first one, then change the remaining bits. So 0, 0 will become 1, 1. So this is the 2's complement of 1. 2, 0, 1, 0. Retain the bits before 1, including 1. So therefore, this becomes 1, 0. And change the next bit. So this becomes 1. This is retain the first one and the rest of the bits before it. So therefore, it is the same. This one, retain this one, change this 2. That is 0, 0. This time, there are 3 inputs and we have three possible combinations. With this, let's extract the equation. Let's try to use a K-map. So for x, it will be equal to 1, 2, 3, and 4. 1, 2, 3, and 4. How many groups do we have? This one has no adjacent prime with it. We can have 2 and 3, then 1 and 3. So therefore, x will be equal to this, which is A, B prime, C prime. Then we have the blue group that will be A prime, B, and the yellow group will be A prime, C. So let's deal with Y. So Y will be 1, 2, 5, and 6. 1, 2, 5, and 6. How many groups? We can have these 2, they are adjacent, and these 2 also. So there are 2 groups. Therefore, X will only be equal to, this one is B, C prime, and this group will be B prime, C. We try to observe this equation, however, it is the equation for an XNOR. So that becomes X, therefore, is equal to B XNOR C. How about Z? So Z we have 1, 3, 5, and 7. 1, 3, 5, and 7. So that will be equivalent to a single group. Therefore, X will be only equal to C. Let's try to implement these 3 equations now for us to be able to get the circuit for a 3-bit 2's complementer. We have 3 inputs. We have for X, A, B prime, C prime, A, B prime, C prime. Then we have A prime, B, A prime, B. Then we have A prime, C. These 3 are ORed together, produce X. Then we have Y is equal to B XOR C. B XORed with C is equal to Y, and Z is equal to C. We can use, however, here a buffer for us to implement Z. Let's simulate our circuit. Let's get, for example, 2, 0, 1, 0, 0, 1, 0. If this is 0, 1, 0, what will enter here? Since this is already 0, then this will be equal to 0. This will become 1, and this will become 1. So this will be 1. So therefore, X will already be equal to 1. What entered here is 0, 1. So 1, 0. So this will also be equal to 1. 0, 1, 0. So this will be 0. So 1, 1, 0. For 2, that is 1, 1, 0. What else? And let's try to simulate 6. 1, 1, 0. 1. This is 1 also, it becomes 0, so this is no 0. This is 1, so this will become 0, so this will be 0. This will be 0, so this will also be 0, so therefore this is 0. So 1, 1, 0, so 1 and 0, so this will become 1 because they differ. So 1, 1, 0, this is 0, so 0, 1, 0. 0, 1, 0. These are three other very important circuits inside our computer, and would be needing also the circuit in the design of more combinational circuits, and we'll be using them also in the design of sequential circuits. See you again on my next video.